So our next presentation is going to be by Michael John Caola, if I'm pronouncing it correctly, I hope. And Michael has a bio that's on the thing here, and perhaps I can let Michael tell us a bit about himself and then begin, right? So I'm just going to hand it off to you now, Michael, okay? Are you ready?
He's muted now.
Okay, very good. Now you're muted, so please unmute, and then we can begin. So, very good.
Text board.
First slide, please.
All right. One moment. Yep.
Ah, there we are. Good. Okay, the top line. No, this is not the first slide. I think this is the last slide. This is, yep, good. Right, first slide, it's up. Good. Now, the top line are the integers 1, 2, 3, 4, 5, which, according to Chronica, were created by God. Some of these integers are special, they're prime. A prime integer is divisible only by 1 and n. Thus, integer 31 is prime, but integer 30, which equals 2 times 3 times 5, is not. Now, any n is, miraculously, a product of primes. And our choice, alpha I, there, is to be commended, because with n to the power 0 equals 1, and 1 times 1 is 1, this leads to helpful significations in calculation. Next slide, please. Right, now we want to count the number of primes in the range 1 to n, and this prime counting function perversely is called pi, as in circles. Right, so above, pi of 22, which is the number of primes less than or equal to 22, count, equals 8. Pi is a famous number, a name. Mathematicians have all had something to do with number theory and with pi. Names like Riemann, Hadamard, de la Vallée, Poussin, Hardy, Selberg, and many, many others. Now, on a computer, pi has been calculated for argument 10 to the power 29, which is a big number. There has been great computer algorithm ingenuity and advances, and one can say that modern number theory is pencil on paper analysis plus computers. They go hand in hand. Our presentation contains a novel derivation by iteration of Legendre 1808. Next slide, please. Both Spencer-Brown and Caola seem to have an eye and a nose for this 1808 wonder formula. Spencer-Brown is to be congratulated on his good taste. Legendre's 1808 useful analysis is of the sieve of Eratosthenes, which is 200 BC. The Möbius function you see here is a little mysterious, like his strip, and it now pervades number theory. use of iteration here is novel and unusual in number theory. Our pi of n, Caola, seems superior to Riemann's complicated explicit formulae. Next slide, please. The Schoenfeld inequality of 1976 is an alternative statement of the Riemann hypothesis QV, RH. The computer algebra system Mathematica 12.1 says that this alternative is true. Stephen Wolfram, please comment. Next slide, please. Right. Sorry. Okay. A recent archive article by Flagg, Kaufman, and Sahu is a detailed analysis of Spencer Brown's purported proof of the Riemann hypothesis. If this proof is accepted by the Clay Institute, then Spencer Brown's estate will be credited with $1 million. It seems uncontroversial to say this proof is not yet fully accepted by mainstream conventional mathematicians. Next slide, please. Now, the Riemann zeta function itself. The proof of the Riemann hypothesis has eluded the world's best mathematicians since 1859. Riemann's great advance over Euler's previous brilliant input was to replace the argument of pi from x to x plus iy. Thus, he moved the analysis into the complex domain and brilliantly used the recently acquired tools of complex function analysis to do his 1859 paper. That is the end of my presentation. Thank you.
Wow, thank you very much. That was beautiful. That was really nice.
Thank you.
And of
Okay,
course,
I'm here for the flood of questions.
Yeah, we have one hand in the room now, okay, and that belongs to Sahu. I think he's going to tell us how he will distribute the $1 million to all of us.
No, not. That's my question is. You mentioned the alternative, Schoenfeld inequality. Could you tell us a little more about
Schoenfeld's inequality? The reference is in the paper, so you can look at it. But
okay.
Yes, it's apparently, if the Schoenfeld inequality holds, then the Riemann hypothesis is true. So I've fed this into computer algebra system Mathematica, and it says yes, it's true. Now, that seems absolutely great, but the comments of Stephen Wolfram, who is at this conference would be valuable.
Virtually, yes.
And
Oh,
not
excuse me, could I see your
Yeah.
previous slide?
This one?
This
Sorry,
one?
sorry.
Oh, that was just the previous slide. Yeah. All right.
Was that
The
the one?
slides are being.
Do you have a slide with what you call the Schoenfeld inequality?
No, I don't. But it is in the paper.
Okay.
Okay.
I will share. I will share it with.
All right, very good. Yeah, someone in the room here will be distributing that, so we can all have a look.
It's ref.
Lou, do
Lou wanted, I think,
yeah, I
a
think
comment.
you have a comment, Lou, or a question as well?
I have the following comment about analysis of proofs by Spencer Brown. Spencer Brown would often say, I have a proof of this.
Yes.
You must understand that that means that he has a structure that is completely convincing to him.
Yeah.
And he is a very strong and deeply observing mathematician. So one should respect the statement and ask the question, what was it that convinced him? Because after all, a given text is very difficult to read. This has been our attitude and continues to be our attitude toward all of his writing.
Yeah.
People out normally, when they say they have a proof, mean that not only do they have something that convinces them, but they have written it up in such a way that they believe will convince others.
Yeah.
And Spencer Brown, when he says he has a proof, means that he's convinced.
Yeah. His proof has been published in the latest edition of Laws of Form.
Yes,
This
indeed.
is the 6th English edition, and it is Appendix 9. And I may say for myself that by training and what I know mainly, I am a mathematical physicist. I am an amateur dabbler in number theory and, if I may say so, Spencer Brown's Laws of Form. So it was really meant to say that not everybody would say or agree, competent people, not myself, that Spencer Brown had done, because, I mean, proof.
Well, yes, of course. But that's what I'm saying. That you have a text and you have the fact that this person was convinced, and in his writings he tells you why he is convinced if you read it carefully.
Yes.
Then you have the task of finding out if you're convinced and what further work you need to do in order to become convinced.
Yeah, sure.
I won't make further comments about that. Sahu and I will be talking about some of that later.
Right. Good. Yeah, I just still wish to say I'm quite an amateur in this, and it was really meant just to reflect my apparent reading of the way the outside world possibly saw it. But I agree with you. I mean, yep, here's Appendix 9. Is there for everybody to study, including the Den-Joy hypothesis and so on and so on. And I am frankly mathematically not up to it, but other people are. Yes, I mean it's quite it's an enormous achievement if he has done that and the world becomes convinced, then that is an amazing mathematical achievement. Yep.
A question from Lyle. Lyle, do you want to voice your question?
One of the things that struck me in the latest edition of Laws of Form was his comment that if something turned out to be really hard to prove, that it was usually because it was very close to an axiom. And so the question is, what do you get if you take the Riemann hypothesis as an axiom? Is there something significant that we can learn from
Yeah.
what that would be as an axiom.
Thank you. Again, I'm just saying I'm an amateur, but I can appreciate that people who take this not much more seriously, but have studied it much more deeply than my superficial thing, are asking questions like that. I wish I could answer you positively, but yeah.
But I think Lou and I could, or Jim could probably talk about, there are many statements that if the Riemann hypothesis is true, what follows from that, and there's many statements that are like those like sort of implications that if the premise is if RH, then so and so and so, and there's a whole bunch of people working on that. Although I just want to say that I'm in deep appreciation and admiration that you also used the Legendre formula, which is an absolutely beautiful way
Yes,
and I think that just meditating on that formula, whether or not he has a proof of the damn thing, like, I mean, that's a different question. But like, if we just study the formula and the fact that you used it as well,
Yes.
is really
I mean,
amazing.
I've called it here the wonder formula. To me, it really is a sort of deep entry into serious number theory. Spencer Brown, and I've said he's a clever fella, we've both seemed to have started with that formula. Appendix 9 starts with that formula and goes on via the Möbius function with his proof of the Riemann hypothesis. I used my analysis and derivation of a new prime counting formula, make a comment on the Schoenfeld inequality, and merely say that if you run this through Mathematica, it says it's true.
I have a question about that.
Yes.
I'm looking at your paper, and you said that the command in Mathematica that you handed it was you run over x, and x goes between a certain number and all the way out to infinity in
Yes.
the formula.
Yes.
But Mathematica is not capable of doing calculations on an infinite set, so it must do something, either truncate or something, right? When you ask it for the truth value of something which is quantified over an infinite set. Do you know what Mathematica does under those circumstances?
No, specifically I don't, and that is why I'm asking Stephen Wolfram,
I would make a guess that it truncates at some point. In which case you probably have verified that it's true for a very, very large range of x.
Well, that isn't what it says. That's all.
I realize that.
Yep.
But Mathematica is not like, Mathematica doesn't make higher level arguments like we do that could use induction or something and actually tell about an infinite set.
I think if we ask Stephen Wolfram very nicely, it is possible, I think, in principle, to have introspection on the process. You might find that there is an error term and there is possibly an assumption being made about how that error term behaves, because this is the cutting edge of Terence Tao's research on exactly these counting primes and field squares. So it will come down to what is the behaviour of this error term. That error term is intrinsically linked to the distribution of primes, which is...
It's, well, the answer is I don't know, and I would be fascinated to hear what Stephen Wolfram might have.
Yes, very interesting to hear what he would say about that.
Yes.
I don't know if he would.
Okay, well, very good. I think that Stephen Wolfram will get to hear all of this, right? So,
He said he's open to questions.
yeah, very good. Okay, any other questions? We have until 4:15 is Bruce's talk. So,
Does anybody have Mathematica? on
You
their
can run a
laptop.
Mathematica on the
don't
Raspberry
know.
Pi.
Yeah.
There's Mathematica.
I don't have a license. I just have a pirated copy that's on my other
take
laptop.
it.
Oh, is it? Okay.
Okay, so I think that I think we'll take a 5-minute break now, and at 15, at quarter after, we'll be here again for Bruce's talk.
Don't tell Steve.
Thank you, Michael.
Yeah, thank you so much, Michael. Let's get a round of applause.
Thank you. Okay, bye.
Thank you. Bye. That was a really lively conversation.